Today I'll be presenting my analysis for lab for oscillations of spring mass system. In this lab, I use video analysis in Tracker and a computational model in Python to examine the motion of a mass oscillating on a spring in 2 dimensions. My primary focus was to determine if the energy principle is satisfied within this system by comparing my experimental observations to my theoretical predictions. To start, I define my system as the mass, the spring, and the earth. By including all three, we can treat gravitational and spring potential energy as internal. I assume the surroundings had no significant interaction with our system, meaning no external work is done. I use Newton's second law to iteratively update the object's velocity and position, and the energy principle to check the conservation of energy throughout the motion. The model was initialized with a mass of 0.402 kilograms and the starting position found in Tracker. I calculated the spring constant and relaxed length based on the period of oscillation and the static equilibrium of the spring. These constants allowed the code to accurately calculate the spring force, which is force equals negative k times s times L hat. Here I'm comparing my computational model's predictions on the right with my experimental data from Tracker on the left. If you look at the time intervals between the peaks, you'll see they are nearly identical. My model successfully captured the period of the oscillation, confirming that the spring constant and mass I used in the code were accurate to the real-world setup. So is the energy principle satisfied? Looking at the graph, the answer is yes. While the kinetic and potential energies shown in blue, red, and green oscillate significantly, the orange line representing the total change in energy remains at 0. This confirms that for our chosen system, no energy was lost to the surroundings, satisfying the energy principle. Finally, I used the experimental data from Tracker to estimate the oscillation periods. By averaging the time between several peaks, I found the x period to be 1.646 seconds and the y period to be 1.520 seconds. Even though this is one mass, these two periods are different because they are driven by different physical mechanisms. The vertical y oscillation acts as a mass on a spring, while the horizontal x oscillation acts more like a pendulum. Because these two tempos don't perfectly match, the mass creates a complex, shifting 2D path rather than a simple circle.